Assalamualaikum warahmatullahi wabarakatuh. A very good day to all. And today we will be learn on the learning unit 4, which is the introduction to organometallic chemistry. Okay. Before we start, we look at the learning objectives of this lecture. There are three learning objectives that we need to achieve at the end of this lecture. The first one is to define what is organometallic compounds. Okay. The second one is to understand the back bonding concept, and last one is to understand the 18 octet rules. Okay, we need to achieve these three items at the end of this lecture. Okay, the first one, organometallic complex. What is organometallic complex? It is the complex that contains the metal carbon and the metal hydrogen bond. Okay, if you have a metal carbon bond and a metal hydrogen bond, then the compound is known as organometallic complexes. Okay, the early were found for the main group elements, which is the S and P block element of the periodic table. Or what we can say, it comes from the group 1 to 2 and group 13 to 18. Okay, that is the early organometallic complex found. Okay, the common early examples are organolithium, organomagnesium, and so on. Okay, the complexes the metal come from the main group element attached to the carbon or hydrogen. Then we call them as, for example, if lithium is attached to any carbon molecules, we can say the complex as the organolithium. If the magnesium attached to the carbon or hydrogen molecules, it is known as the organomagnesium, or I bet all of you have heard about the Grignard reagent. Okay. The organometallic complexes from the main group element, they are widely used in the organic chemistry for the formation of the carbon-carbon bonds chemistry. And these are the common example, which is what we call as Grignard reagent. The reaction between the carbon with the halogens, okay, halogen, and in the reaction with Grignard reagent, we produce carbon-carbon bond here. Okay, and however, the main group organometallics are normally stoichiometric reagents, where you have for example, 1 mole react with 1 mole, we can get a product. Okay, but then different with the organometallics from the transition metal. The transition metal organometallics usually used as the catalyst, where we can recover back the organometallic. Okay, it as the organometallic from the transition metal can be reused. Okay, as a catalyst and can be reused. Different from the organometallic from the main group element, it is a stoichiometric reagent. In a chemical reaction, the amounts of catalyst needed are usually in a very small quantity. For example, 1 mole percent. Okay, of the total percent of the reactant, only we use about 1%. Okay, therefore, the use of catalyst avoids the waste formation associated with the main group reagent. Okay, therefore, if you use the catalyst, we can avoid the waste formation compared with the main group reagent. And these are the example of the catalytic application of organometallic complexes. You look here, it is a dicobalt dicobalt octa-carbonyl, okay, for the hydroformylation catalysis in 1930s, where it was found by Richard Heck, and the reaction mechanism has been shown below, where actually the hydroformylation catalysis is for the production of aldehyde, where it actually involves 7 steps. The first one is the addition of the hydrogen to produce the cobalt tetracarbonyl, and then the removing of the carbonyl here to produce this intermediate. Then later the CO has been added again so that it can be attached at this position here. Then another carbon triple bond O molecules added and it attached at the position here. Then at last we add hydrogen so that the hydrogen will be attached at these two positions here. Then the aldehyde has been produced and we can get back the catalyst here. It can be reused, regenerated and reused. Okay. Apart from the catalysis application, okay, the organometallic complexes has been used for photophysical application due to its luminescent properties. Okay, it has been widely investigated since late 1950s, and the well-known luminescent organometallic complex is the IRPPY3, which is the iridium triphenylpyridine. It has been used as the organic light emitting diode, LED. Okay, LED, it is kind of a display. It has been used widely for a display device. Okay, for example, here you can see the Nokia. You can click to the link later. Okay, you can see that Nokia 700 has been used OLED for the display device of the smartphone. And the structure of the complexes is like this. Here you can see there are three of the pyridine here. Okay, three structure of the phenylpyridine here. Okay, phenyl group and with the pyridine attached as the ligand to the IR metal complexes. This is fractional and meridional arrangement. Okay, apart from the properties, apart from the application for the display device, the organometallic complexes also used for the bioimaging application in the medicinal area. Okay, where the complex has been used to penetrate into the cells, and it gives the luminescent properties so that we can view the cells. Okay, in our human bodies or in any cells. Okay, in any life being cells. If we compare the organometallic with the normal organic fluorescent dye, the organometallic complex has more advantages. For example, it has a longer luminescent lifetime. You can view the luminescent more longer. Okay, and also it has bigger Stokes shift, which enables them to give a good emitting or fluorescent properties. And these are the example of the complex that has been used for bioimaging purpose. Okay, these are the example of the complex. Okay, we've done with the introduction. Then we move to the back bonding concept, where actually the back bonding concept is to give the explanation on how different complexes have different stability. Okay, it actually depends on the types of ligand. Okay, the types of ligand. Okay, some ligands such as ammonia, they are good donor. Okay, they are good donor, but they are not as significant except because of the single bond between NH and no other additional orbital to accept electrons at the ligand or on the ligand. On the other hand, the carbonyl group C double bond O, they have two types of bond, with sigma bond and pi bond. It is a good acceptor because of the additional orbital for them to accept another electron. Okay, they tend to be a very high field ligand and form a very strong MC bond. Okay, the lone pair electron from the carbon atom donate to the empty D sigma orbital to the metal and form an MCO sigma bond. Okay, this is the bond where the carbon atom donate to the d pi orbital, okay, to the metal ion and form a sigma bond. Okay, and at the same time, the empty p pi orbital in the carbon atom accept electron from the d pi metal and form a back bonding here. Okay, you can see here actually there is sigma and also pi bond. So the empty pi bond here accept 2 electron from metal, thus forming bond. This is what we call as the back bonding phenomena. Okay, it's actually a key feature of ML bonds, where L is an unsaturated ligand, means that it must be more than one or single bond ligand. Okay, WL6, for example, the tungsten organometallic with 6 coordinated ligand, okay, it is a good example to show the stability of the complex due to the back bonding. If you look these two cases, where the first case is we use ammonia as the ligand. Okay, since ammonia is a good donor, the tungsten has 6 electrons in the d orbital, and the W and H3 bonds are purely sigma bond from the ammonia ligand, okay, which cause the complex to become unstable and very air sensitive, unstable because of no back bonding happen. On the other hand, if L used for the complex is the carbonyl with the C double bond O, another extra bonding pi bond, okay, it will cause this complex become stable because CO can accept electrons from the metal center via back bonding and thus make the tungsten CO bands become strong. Okay, the phenomena can be explained or can be investigated by looking at the IR spectroscopy of the compounds. Okay, the IR spectroscopy can be used to investigate the involvement of the pi star orbital of the CO in back bonding. How is it? Okay, if CO are bound to the metal, okay, CO bound to the metal, okay, only by carbon lone pair electron and no electron back bond to the metal, the frequency in the complex would be almost similar to the free CO. Okay, you can see the free CO, they have their own value. If only CO attached to the metal without back bonding, the frequency would be almost similar to the free CO with maybe a little bit 2 or 3 difference. Okay, 3 unit difference. Okay, we look at the example. BH3 is a PO electron acceptor with empty p orbital in the boron atom. Okay, is empty of the boron atom. When BH3 react with CO, the reaction gives H3BCO as the product. The frequency of the free is 2149. Okay, but the CO frequency is 2178. Okay, therefore it indicates the resulting CO has higher energy. Okay, meaning that what happened is the CO has higher energy compared to the free CO. Okay, contrarily, the frequencies of CO for the CO in a metal complex shifts to a lower energy region. Okay, why? This happened because of the weakening of the CO bond at the pi star orbital. Okay, the weakening of the CO because of it is filled, so the CO bond become weaker. Therefore, the value of the CO frequency is lower. And we can see for the vanadium, chromium, and manganese, the trend is increasing when we move from the left to the right. Okay, the value is increasing. Okay, the more electropositive of the metal, we can say that the number of the frequency values is lower. Okay, if you look at this position, the position of vanadium, it's located more to the right. More to the right means it is more electropositive. Then you can see that the frequency value is lower. Okay, more electropositive means it means that it can donate the electron very well. Then thus the number of frequency values will become lower. Now we move to the 18 electrons rules. Okay, several ligands may bond through different numbers of atoms to metal. Okay, how it can bond to the metal? We look at the number of here, the number of formula here. Okay, the number of atoms through which a ligand bond is indicated by letter eta. Okay, the superscript indicate the number of atoms attached to the metal. For example, 1 means that monohapto. If 3 is trihapto and 5 is pentahapto. Okay, you can see here there are different number attached to the eta here, and what does it indicate is the amount of atom attached to the metal. Okay, hapto is actually means fasten. Okay, therefore, if you say it is trihapto, it is fastened at 3 places. And the table below shows the common organic ligands with their names. You can see here carbonyl is the one of the commonly used ligand. Carbonyl, carbene, carbine, cyclopropenyl, cyclobutadiene, cyclopentadiene, alkyl, allyl, acetylene, ethylene, 1,5-cyclooctadiene, and benzene. Okay, and also some ligands, they are the bridging ligands. Means that they bridge between two metal centers. For example, here chloro and CH2 here, it acts as a bridging ligand where it combine or it bridge between aluminum and titanium. In this case, the Cl is actually bonded to the atom by donating their electron, but at the same time it accepts electron from titanium. Okay, the mu has been used to indicate the number of metals atoms bridge. In this case, the chloro attached with 2, which is aluminium and titanium. So aluminium mu2 chloro, mu2 also CH2, then titanium CP cyclopentadiene with 2 molecules of cyclopentadiene. And this table, it shows how it shows the electron counts for different types of ligands, where X refers to the ligand with negative charge, L refers to the neutral ligand. If you look at this table, there are different types of ligands with different properties. The ligands CH3, Cl, PHH, and allyl, they are the negative charge ligand X with 2 electron counts. Okay, if you see the CH3 means it comprises 2 electrons. Okay, lone pair donors here, carbonyl, ammonia, triphenylphosphine and trimethylphosphine, they have 2 electrons, and they are the neutral ligand. And you look one by one here. Benzene is a neutral ligand with 3 sites of attachment, and they have 6 electron counts. 5 for the cyclopentadiene, they are actually both, which is the neutral and also negatively charged ligand. Okay, it's actually the structure is looks like this, where this is the negatively charged ligand, and the other 2 sides is for this is the neutral ligand. Okay, these are some of the examples. You can look through this one and look at the electron counts. The electron counts will be used for us to calculate the 18 electron rules or the electron counts of the complex. These are the examples of how to count the electrons. If you look at these compounds, which is the dicyclopentane ferrum ion or ion complex, where Cp, if you look at the previous table, the Cp has 6 electrons each. So if you have 6 electrons here, if you have 2 cyclopentadiene electrons, so 6 plus 6 is 12, plus 6 electron from Fe2 plus. How to get the 6 electron? If you look at the electronic configuration for Fe, it's actually the outermost electron have 6 electron, then it remove 2 of its electron, become 6 electrons. So 6 plus 6 plus 6 is 18 electron, and this is obeying the 18 electron rules. Now we move to the molybdenum complex, where MO4 plus, because how we get MO4 plus, you look at the electronic configuration of molybdenum. The neutral molybdenum has 45 and 5s1 at the outermost electron. So when it is attached with 4, and when the charge is 4 plus, so it removes 4 of its electrons, so the remaining electron is 2e2. And 2 plus the 8 electron come from the 4 hydride ion here. 4 times 2 electron is 8 electron, and the electron for the trimethylphosphine is 2, so 4 times 2 is 8. So 8 plus 8 is 16 plus 2, 18 electrons. So it also obeys the 18 electron rules, and thus it is a stable complex. Okay, so that's why we need to count the electron. But then for the some of the complexes does not obey the 18 electron complex, but then they are also a stable complex. For example, this nickel 2 plus complex. The nickel 2 plus attached with the C3H5 ligand. There are two ligands. So each of the C3H5 has 4 electrons. 4 times 2 is 8 electron. 8 plus 8 is 16 electron. How to get 8 electron? As I mentioned earlier, you need to look at the neutral nickel first. Neutral nickel has 3d8 for S2 at the outermost electron. So remove 2 electron. The remaining is 8. So 8 electron plus 8 electron is 16 electron. Although the 16 electron is not obeying the 18 electron rule, but then the complex is also stable. And most of the complex with the geometry square planar and tetrahedral, they will they will not obey the 18 electron rules. For example, and next is the molybdenum complex attached with the two molecules of benzene, where molybdenum 0. So the electronic configuration for the outermost electron is 6. So 6 electron here, and each of the benzene give 2 electron have 6 electrons. So 6 times 2 is 12. 12 plus 6 is 18. And at this titanium 4 plus, how to Cl attached with the chloro and 2 molecules of chloro and 2 molecules of cyclopentadiene. So Ti4 plus, the neutral configuration of Ti is actually 3d2 for S2, and if it remove 4 of electron, so the total electron is 0. Okay, 0. The Cl minus, 2 of 2 Cl, so 2 times 2 is 4, and the cyclopentadiene is 6 times 2 is 12. 12 plus 4 is 16. So this also not obeying the 18 electron rule. Next is the cobalt 3 attached with 2 cyclopentadiene ligand. Okay, CO3 plus. The outermost electron is actually 9. 9 minus 3 is 6. 6 electron. Plus with the 2 times 6 electron come from the cyclopentadiene. So 6 plus 12 is 18. This is how you calculate the electron count for a metal complexes or the metal compounds, coordinated compounds. So next is the exercise for you to do. They are A to H, so you need to calculate the electrons of the following complexes. What you need to do is, this is for your attendance. So you need to complete all of this exercise, and I will give you a link for you to submit only the answer of this exercise. Then we will discuss on this later in next lecture. So I hope that all of you can complete this exercise today by 5 p.m. as your attendance. And we will discuss the answer next Tuesday during our synchronous session. So I hope you can understand this lecture. If you have any hesitation, you can just contact me through WhatsApp or email me. Then I'll look if whether we can I can give you a better explanation. And I think that's all for our lecture today. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.